So this week we're going to do simulation in SAS instead of just in Excel. And I know that I don't have the PowerPoint presentation in presentation mode, and that's because I'm going to go back and forth between this and SAS. So just bear with me. But we're going to do 4 examples in SAS. One of them is a little harder and probably a little tougher than what I would expect you to be able to do on your own. But the first 3 are for sure things that I would expect you to do. So the first one, we're going to simulate the roll of a single dice, or single die, probably should say, 1,000 times, and then use this to calculate the expected value of the dice. So the expected value is going to be the number that you expect to happen. So kind of the average is what you want to think there. So if I go to SAS here, I'm going to call this something. So I will call it data die roll. So I'll do that, and let me make this a little bit larger so that you can see it a little bit better. There we go. So next, we're looking for the average value, which means that we're going to have the average value and then also a sum of all the dice. So I'm going to start with the average value equaling 0. And then I'm also going to start with the sum being 0. So this is kind of our starting point, and that's what I'm telling SAS is just, this is our starting point. Average value is 0, sum is 0. And then we're going to do what's called a do loop. And a do loop is where you tell SAS to do this a certain number of times and then spit out the output each time. So I'm going to say do from I equals 1 to 1,000. So what SAS is going to do is it's going to do 1,000 times what I'm about to tell it to. So what I want it to do is first make a roll. And the roll is going to be a random integer from 1 to 6. So if you want SAS to spit out a random integer from 1 to 6, there's the command for it. You want to put integer in quotations and then 1 comma 6. It knows to include 1 and 6. Okay, so that's the first thing. Now we're going to say after you roll, add that to the sum. So this line is saying the previous sum, add that roll that just happened. So in the beginning our sum was 0, but now we've said add the previous roll to it. Then the average value, again, that was 0 in the very beginning, but now we're saying it's our sum divided by whatever trial we're on. So if we've done this 500 times, what we've done is we've added up the first 500 rolls, and then we've divided it by 500. So if I was equal to 700, that would mean that we've added up 700 of these rolls, then divided it by 700. So you'll see that we're going to be doing this from I equals 1 all the way to 1,000. And then we'll tell SAS to output, and then lastly to end all of this. So it's going to output each of these trials, and then we'll tell it to end. So let's run this. And I'm not really interested in the very beginning. I want to go to the very end. There we go. So in the very end, so this is after I've done 1,000 trials, the sum was, you can see here, 3,524, and yours is not going to be exactly like mine. Yours should be close, but it's not going to be exactly like mine because this is all random. And then if I scroll back over, the average value was 3.524, and that's the number I was looking at. So what is the expected value for rolling a die 1,000 times? You expect to get 3.5. Now, I know that's not possible, but that's our expected value. Kind of following along with this example is I want to start asking the question, if I roll a single die 1,000 times, based on this, what's the probability of rolling a 6? Okay, so what I'm going to do is I'm going to go back to SAS, and remember we're looking for the probability of rolling a 6. So let me open a new program. I'm going to again call this die roll. You can call it whatever you want. For the probability of rolling a 6, what we want to do is out of the 1,000 trials, how many of them are 6, and then divide that by 1,000. So that's what we're going to be doing. We just need to count of these 1,000 trials, how many of the rolls were 6s, and then divide that by 1,000. So what I'm going to say at first is that we haven't rolled any 6s. So I'm going to call it num6, call it whatever you want. I'm going to say in the beginning of all this, we haven't rolled any 6s. Then I'm going to do 1,000 trials. So on these 1,000 trials, every time I want to roll, so this is the same command as last time. I want to roll a random integer from 1 to 6. And then I want to start counting, but I only want to count the rolls that were 6. So I'll say if, this is an if then, so if the roll was equal to 6, then do the following. All right, so we're going to fill in the blank here. So if the roll was equal to 6, do something, else do something else. And every time we do one of these, we need to end it. So the way this if-then loop works is that if we roll a 6, do something. Otherwise, that's my else do something else. Okay, so if we roll a 6, then I want to say I just rolled one more 6. So I'll say the number of 6s has increased by 1. So if we rolled a 6, then the number of 6s should be the previous number of 6s plus 1. Otherwise, keep the number of 6s equal to the number of 6s. So in the if-then loop, we say if you roll a 6, increase the number of 6s by 1. Otherwise, keep the number of 6s at the number of 6s. So that's going to give me the number of 6s. But what we're looking for is the probability of 6. So we'll say it's the number of 6s divided by that 1,000. And again, we want to output all this, and I also want to end all of this. So the probability of 6 is the number of 6s divided by 1,000. Just like before, I'm not really interested in the beginning. We're doing a lot of trials so that I can see kind of what happens overall. So if I'm reading this, out of the 1,000 trials that we just did, 177 of those I rolled a 6. Yours is probably a little bit different, and that's fine. Which gives me this probability in my lower right-hand corner of 0.177. And yours should be pretty similar to that. I mean, it might be slightly off, but we all should be around 0.18 if we round up. Again, it'll depend. If we wanted to do more trials, we could get an even better number. I know the question didn't ask for this, but let's say I change the number of trials to 10,000. And go all the way to the end. So 0.17 is what we're going to get out of 10,000 rolls. The probability of rolling a 6 was 0.17. Okay, now we'll look at this contractor's problem. So we have 3 contractors. They're all bidding for a job where the lowest bid will get the job, right? So the person who's going to be the cheapest is going to get the job. The way that they bid is that contractor A is going to bid between 600,000 and 800,000, and it's uniform. So there's an equal chance of any number between 600,000 and 800,000 happening. Contractor B is going to be a normal distribution. The average is 700,000 and then standard deviation 50,000. So he's really likely to bid between 650 and 750. And then contractor C is always going to bid $750,000. So what's the probability that contractor C wins the bid? So we're going to do 1,000 trials. So pretend like there were 1,000 jobs. What's the probability that always bidding 750 gets you the job? So we're going to go over here to SAS one more time. We're going to name something. I'm going to call it contractor. Now to start off with, we need to say how many bids has C won. So I'm going to say in the beginning, I'll call it number of C. In the beginning, the contractor C has won 0 of the bids. We want to know of the 1,000 that I'm about to run, how many of those is he the lowest? Then based on that, find the probability. So this is that do loop again. So do from I equals 1 to 1,000. We're going to do some stuff. And we might as well close the do loop from there. It's kind of just a good habit to do that anyway. So every trial, this is every bid, every time A is going to be some sort of random number that's uniform between 600,000 and 800,000. So that's A's bid, is some random number. It's uniform between 600 and 800,000. B is going to bid based on a normal distribution. The mean was 700,000 and the standard deviation was 50,000. And then C equals 750,000. So all that's doing is their bids. In fact, what we could do right now, let's just see if we can view this. If I go to my output data, ignore the number of C. So for the first trial, contractor A, his bid was 755,804. Contractor B was 791,000, and then contractor C was 750,000. So based on this first trial, C should win. We haven't told it that yet. All I've done is say, do 1,000 trials. This is how they're each going to bid. So you can see these are the 1,000 trials of how each of them has bid. Every time C is 750,000, A is uniform between the 600 and 800, and then B was centered at 700 with standard deviation 50,000. So now let's go back to our code. Based on that, I want to say if C is the lowest, add 1 to the number that C should win. So we'll say if C is less than A and C is less than B, then we'll do something and we'll end it. So if that happens, we'll do something and end it. Otherwise, we'll do something else and then end it. So on this first one, if C is less than A and C is less than B, so that means that C is the lowest of the bids, then the number that C wins should be the previous number of C plus 1. So I'm increasing the number that C wins by 1. Otherwise, the number that C wins should remain the same. So what that's going to give me is how many of these bids has C won. So why don't we just run this and see. I'm going to go to the very end. So number of C, if I scroll down, it looks like out of the 1,000, C has won 36 of the bids. This I is telling you which trial we're on, so which job, and then again, A, B, and C are the bids. So that's just the number that C has won. But remember, I want the probability. So I'll say the probability of C was the number of C divided by I. I guess we could say I. That'll give us a different number every time. But we might as well just say 1,000 because that's the one that I want. Output all of that, and let's see what we get. We should get the number of C divided by 1,000 that we just did. And these are not the same numbers I had last time. But if you know why, it's because it's a random number generator every single time. So the probability of C, I got 0.046. Now doing more trials would probably give you a better estimate, but there's our estimate for the probability that C will win just by bidding 750,000 every month. And this bonus problem, which I misspelled activities. So a project has 3 activities. We